Picek is an assistant professor in the cybersecurity group at TU Delft in the Netherlands. His research interests are security and cryptography, machine learning, and evolutionary computation. Before the assistant professor position, Stjepan was a postdoctoral researcher in MIT, USA, and at KU Leuven, Belgium. He finished his PhD in 2015 with a topic on cryptology and evolutionary computation techniques, and he has several years of experience working in industry. So today he'll be sharing his knowledge upon the use of machine learning for assessment of side channel attacks. And so I would now invite you to please take the floor. This mic, please share the work with us. Stjepan, I think you are muted.
Okay, so thank you very much for the nice introduction. Can you hear me okay?
Very well now.
Okay, excellent. So thank you to Avi and Shivam for inviting me to give this talk. So the title of the talk is on use of machine learning on using of machine learning for assessment of side channel attacks. So I will be talking about several topics or subtopics. So some stuff that I consider to be relevant and interesting at this point of our community understanding of side channel attacks and machine learning. Of course, there are many other perspectives, and if you have any questions, please do ask. I will do my best to and try to answer them. Every work here is done in collaboration with many of my co-authors. I will mention them more as we talk about the specific topics. If you are interested in any of these topics, I also provide links about the papers, and the presentation will be available for download. I presume Shivam will organize that somehow. And also there are quite a lot of materials of what we do in the lab of my group, so www.iclab.com. So let's start. Yeah, we already, Sylvain mentioned side channel attacks. So let's first go one step back and discuss what are the implementation attacks. So implementation attacks are all those attacks that do not aim at the weakness of the algorithm, but on the weakness of the implementation. And commonly people mostly discuss implementation attacks in the perspective of side channel attacks and fault injection attacks. And side channel attacks are passive, non-invasive attacks. What does it mean? Passive means the attacker simply observes something, and non-invasive means he does not meddle or change or anything with the target. And actually today, side channel attacks are one of the most powerful categories of attacks on crypto devices. So compared with many crypto analytical techniques, side channel attacks can bring quite significant attack performance. And when we talk about side channel attacks, a common division of those attacks is into non-profiled or direct attacks and profiled attacks or two-stage attacks. What's the difference? In profiled or two-stage attacks, we assume that the attacker has access to a clone device that is basically identical to the device that we want to attack, and then the attacker learns about that device. So he builds a model in the language of machine learning, or he builds a template in the language of template attack, and then he uses that template to break the actual target. And actually, when it appeared, template attack in 2002, it was quite revolutionary because it was new approach. It was something that was very powerful, and even people realized that the template attack is the most powerful one from the information theoretic point of view. And then there were many, relatively many changes. So people suggested stochastic models, pool template attack, and so on. But at some point, people also realized they can use other techniques. So why can we use also other techniques? Why can we use machine learning? So here I show a common scheme of profile attacks where you can see there are two devices, device under attack and identical copy. And then there is the computer. So we use that to build our model, so building profile model. And then we use that knowledge with some measurements from oscilloscope that obtained traces from the device under attack. And from all that information combined, we guess what would be the secret value, so what would be the key. So looking already at this scheme, you can recognize that when we talk about profile attacks, there are two phases, of course. There is that profiling phase and there is the attacking phase. But what can be also seen is that this maps very nicely to certain machine learning methods, especially those coming from the supervised learning domain. Why? Because what we have as profiling is basically training, and what we have as attacking is like testing. So once people realize this and the interest for machine learning because of the improvements in deep learning domain started to be more and more, let's say, relevant, then we as the community started also using machine learning in our side channel attacks. And at the beginning, we use machine learning more classical methods like random forest, like support vector machines. And we used machine learning not only for the attack, but also for the pre-processing, for the feature engineering, so selecting points of interest and so on. And this all basically what we do in side channel commonly with machine learning kind of maps to these three categories. So it maps either to supervised learning, unsupervised learning, or semi-supervised learning. Mostly when we talk about attacks on symmetric key cryptos, like targets like AES, people explore supervised learning paradigms. So you have some examples that are labeled, and then you use that, you build your model, and then you try to guess new labels. For public key crypto, people were also considering quite some techniques from the unsupervised learning domain, so like clustering. But of course, recently we also saw people use supervised learning techniques for public key crypto. And finally, there is the semi-supervised learning, which is somewhere in the, let's say, in the middle between the previous two, because we have very limited set of labeled examples. And looking at, let's say, the number of works considering each of those three paradigms, supervised learning is today most represented in the community. So most of the works consider supervised learning. Unsupervised, let's say, occurs quite rarely, and semi-supervised occurs extremely rarely. So I know only a few works in side channel doing semi-supervised, and I was also pleasantly surprised when Shivam was discussing semi-supervised paradigm for the hardware Trojan. So this is for the machine learning, and of course, no one stops us to extend this to more recent techniques, to more recent progress in machine learning community. And that progress commonly comes with deep learning. And then more recently, from 2016, side channel community started also to explore, can we use deep learning for side channel attacks? And already from the first results, some techniques proved to be quite capable, most notably multi-layer perceptron and convolutional neural networks. And people really started using them a lot. And why do we like so much to use them? Well, there are many reasons, let's say, but two are very important. First reason is we do not need to pre-process the data. So all that step of selecting points of interest, of pre-processing, what we needed to do before, now we kind of skip. We leave everything for neural network to find. So we leave for neural network to find what is relevant and to use that to make the attack. And the second part that we like about deep learning perspective is that it basically works great. So the attack performance is very good, and such techniques can even break implementations protected with countermeasures. So protected with either hiding countermeasures like random delay interrupt, or masking countermeasures like first order masking or something like that. So this is to give you a general perspective that machine learning today in side channel is, let's say, becoming more and more standard, and from the academic perspective becoming very hot research topic, because of course there is a lot of researchers, many more than in side channel community, doing research in machine learning. And as such, machine learning, deep learning is progressing tremendously. And often it's not so difficult to see what is happening in deep learning community and recognize what could be useful also for the side channel community. So in that perspective, we have, well, almost limitless supply of good ideas from other domains that we can also explore in side channel. And now in next part of my talk, I will be basically dividing, let's say, research into three parts. First part will be deep learning generalization and ensembles. Let's say this is the most straightforward direction, because in this direction, I will simply briefly discuss how can we use deep learning and some very well-known techniques from machine learning to improve the attack performance. So this is, let's say, the most straightforward direction. Doing something from the machine learning community that will help us improve the performance of the attack. And then later, I will be talking about denoising out encoders. This is, let's say, already something a little bit more exotic, because if you remember, I already said with deep learning, we do not need to pre-process the measurements. We do not need to select points of interest. We leave all that for our neural networks to do. But the question is, do we really need to do that? Could we still use deep learning maybe to prepare the measurements, to make the measurements as easy as possible to attack, and then to ease our attack effort? And finally, I will be talking about attacks on public key crypto, where we combine unsupervised and supervised side channel approaches to reach top performance. So let's start with deep learning generalization and ensembles. So when we talk about deep learning or machine learning in general, neural networks, what do we want from our neural networks to do? Well, we want them to be as good as possible function approximators. So our measurements basically, they are a function, and then we want to find a neural network that will approximate that function as closely as possible. And then when we do the machine learning process, when we do the training, the question is, how do we know our results are good? How do we know that what we obtained is good? Well, there are two perspectives. There is the machine learning perspective, machine learning metrics, and there are side channel metrics. And unfortunately, those two categories of metrics do not necessarily agree. So what is interesting is that we are running our training process and we are observing the machine learning metrics. And then in the testing phase, attack phase, we do the attack and we are observing the side channel metrics. So the question is, how can we do our training, our neural network training, and achieve maximum quality of the results? So what we say, maximum quality in the generalization. So what is the generalization? Well, we can talk about, in general, three phases of training process. There is the underfitting. That's the beginning phase where our neural network does not fit the model at all because it's not complex enough. So we did not train enough. Then there is the generalization phase. At that phase, actually, we assume that whatever model we have will generalize well to unseen examples. So basically, this is the moment when we want to stop the training. And then if we do the too long training, for instance, or if there is some other problems, we come to the overfitting phase, where actually our metrics tell us that the performance is excellent on the training set, but the problem comes that the performance on the independent data set, on the attack data set, is extremely bad. So how can we improve our behavior? How can we improve that we are able to stop during the generalization phase. So this generalization phase in side channel must be directly related to the key recovery, because that's the goal. We want to find a model that later we can really break the target. And actually what can be seen quite often if you're reading the side channel works is that the generalization phase starts very soon after you start the training. So reading many papers, people write, we do 30 epochs, so how long do you train? 50 epochs, 100 epochs, but this is all relatively short training time. So we do observe that in our side channel tasks, we generalize quite soon. What is very interesting is that if we look at the accuracy at the point when we really start to generalize, that accuracy can be very low. And actually, even something around random guessing, so depending on the leakage model, for instance, if we talk about Hemingway leakage model, having accuracy of around 11% can already be enough for our attack to work without a problem. So the question is, why is it so? So here I show you two graphs. On the left side, you see the training validation and test accuracy. This is very easy target. So this is something trivial to break. So what do we see? We see as we process more and more epochs, our training accuracy is going up and up, while our validation accuracy goes up very abruptly. So up in the first 25 epochs, let's say, and then let's say stagnates. The same happens with the test accuracy. So already this tells us, look, training accuracy, no problem, it's going up. So our model has enough capacity to learn whatever. But very soon after the beginning of our training, we do not have any more need to train because our generalization started, let's say, around 25 epochs. And on the right-hand side, you can see what happens when you observe the side channel behavior. So in side channel, we look at the probabilities, we sum the probabilities, and what we see for the correct key hypothesis, our density of rank output class probabilities is much higher for the correct key than for any wrong key. What does it mean? It means that our best guesses are correct. So even accuracy would give us large number, so high value. And those values that are less likely to be true as judged by neural networks are actually also unlikely to be true. So there are only a couple of values that neural network says, well, this is probably not the correct key, but it's the second or third or whatever, that is actually the correct one. So already here we can see that if our accuracy is very good, that will also map, of course, to our side channel metric, let's say like guessing entropy or like key rank, simply because many of our best guesses will be correct. And then even if our best guess is not correct, probably the second best guess is correct, or third best guess, or fourth best guess. But going further, the chances that neural network will say something is very low. How does it look like if we go for somewhat more difficult target? So here you can see the behavior for the ASCA dataset. ASCA dataset is today, let's say, almost a standard dataset in side channel community that you need to use if you do a profile attack. On the left side, you again see training, validation, test accuracy. And what do we see? Our accuracy can go up to 90% or more without any issues, while our validation and test accuracy actually already from epoch 10, epoch 20 at most, starts to go down. So even before then, in the previous example, when we started to, let's say, overfit around epoch 25, 30, here we see that our generalization behavior happens extremely soon. So 10, 15 epochs. And what do we see if we look at the key rank output class probabilities? So now you can see completely different effect. You can see that the best guess is for the correct key is still the most likely. So the pink line is still a little bit above any gray line for the best guess, but we can see that the tendency in general changed, and that many already second best guesses, third best guesses, and so on are actually wrong guesses. So this is telling us why neural networks have more and more issues in dealing with more difficult data sets. Well, simply because not only the best guess is wrong, but the sum of guesses is wrong, and that sum of guesses is wrong because many of those second, third, and so on guesses were wrong. So while your accuracy can be good, let's say here it's still good, it's like 20-something%, your key rank can still be bad because the sum of probabilities over various traces will tell you that there is no more clear difference between the best guess and the second best guess. And then when you sum all those values, the differences become smaller and smaller. So the question is, how can we easily improve the behavior? How can we easily improve the attack performance? There are many ways to how to do that. You can maybe use better classification method. For instance, instead of using convolutional neural network, we could have used multi-layer perceptron or this or that, and maybe it would be better. Maybe we could also do a better hyperparameter tuning. So less layers, more layers, this and that. Maybe we could add regularization. Maybe we could do data augmentation. So these are all valid options that people explored, and all those options actually do work. But could we also do something simpler? And our perspective is that we can. So what we do know is that whenever you do side channel experiments, you basically, unless you are trying to reproduce someone else's results, you never stop with only a single experiment. So you always do some hyperparameter tuning where you try to find your best neural network. And then the question is, what happens when you find your best neural network? Of course, you're not sure that this is the best ever, but it's the best from the ones that you explored. And then commonly people use that neural network and report the results. But what we can also see is that why don't we use all those results? So if I run 50 experiments, I tried 50 very good neural networks. Why would I take only the best one? Why wouldn't I take the combined results of 10 best networks, or 20, or even all 50? And this is what machine learning community commonly does with various ensemble techniques. And here I discussed the bagging technique, where you basically create many subsamples of the data set with replacement. And then you train a classifier for each of those subsamples. And then you calculate the average prediction from each classifier. And what do we see? Well, these are the results for the Hamming weight leakage model. I did not go into leakage models, but hopefully you know it. Unless, if not, ask questions, and I will explain details during the Q&A. So what can we see here is that if we do ensembles of 50 or 10 methods, we can get performance much better than the performance for one single best. So consider this situation. From these 50 models, you take one single best one, and this is the green line. But you take 50 models, and you can get better performance. Why do you get better performance? Because with ensembles, you can better generalize. And here we can see actually the results to be in that direction for both multi-layer perceptron and convolutional neural networks. So telling us that if you do ensembles, it's not only limited to a specific architecture. So we can really use different types of neural networks and still obtain very good results. The same happens for the identity leakage model, but here we do see smaller differences regarding the size of the ensembles. Why smaller difference? Well, because identity leakage model has more classes. That means there are more guesses. That means the neural network is anyway less certain of the best guess, and then the values spread out more evenly. But already from these couple of graphs, you can see that combining the results is a very powerful technique, and something that comes almost for free, because you do a lot of experiments. So the only difference is that you just now combine the results of those experiments. And this is just like a short preview. So I list here a link for the full paper where you see many more details about how do you really do the combinations, how do you do ensembles, but also many more results to hopefully convince you that ensembles is a simple technique that works well. Next is the denoiser topic. I find this topic to be, let's say, very interesting because it's very different. And it starts with a simple question. If we talk about side channel measurements, targets, they are commonly protected with countermeasures. And the question is, can we consider those countermeasures as certain sources of noise? And of course, not all countermeasures map so nicely to the noise setup, but many hiding countermeasures basically fit very nicely into description of a noise. So hiding countermeasure like random delay, interrupt, desynchronization, jitter, shuffling, Gaussian noise, this all can be really considered as a noise. And then could we somehow reduce the noise, remove the noise, even before we do the attack? And again, looking at what machine learning community did in last years, there is something called the denoising autoencoder. It's a technique to remove the noise. I will not go so much into autoencoders now, but just as a short introduction, autoencoder has two parts. It has encoder and decoder. The goal of the encoder is to transfer the input to the latent space, and decoder reconstructs the input from the latent space. So what does it do? So think of it, you have your input, you squeeze it, you somehow clean it, and then you return it to the input. And what you have at the end is hopefully something that describes the relevant information, but removes the noise. And in the denoising autoencoder perspective, you do that in a way that your input and output are not identical, but represented by the noisy clean data pairs. So on the one side, you put noisy data. On the other side, you put the clean data, and you say to your encoder, fine, now find me a mapping that produces this kind of effect, going from noisy to clean. So what can we do with it? Here, I show you what happens with Gaussian noise. On the left side are the results when you do, let's say, standard side channel technique to reduce the noise in the sense of Gaussian noise. So when you do the averaging, on the right-hand side, once you do the convolutional autoencoder that we used. And what we can see here is that both techniques work well. Well, it's depending on the technique. So CNN works, of course, the best, and MLP is somewhere in the middle, and template attack is, well, it's barely working, let's say, not even working, because the guessing entropy stays around 50. But averaging does work even a little bit better than convolutional autoencoder. But very interesting result is what happens when you have desynchronization. So for instance, you can see on the left side, if you would try to synchronize with the static alignment, and on the right side, when you do synchronization with the convolutional autoencoder, you can see that convolutional autoencoder gives in an absolute perspective, better results, but also makes various techniques more stable. So for instance, especially interesting is here template attack. So we did not improve the attack performance, but we just cleaned the traces that even simpler techniques can break the target relatively easily. Similar, you can see what happens when we do the random delay interrupts. So here you can even see that frequency analysis as the, let's say, standard technique does not even work well for MLP, or at least we were not able to make it work well. And for convolutional neural networks template attack, it works, but we do see the improvements are small, and we need many attack traces to break the target. On the other hand side, if we use autoencoder, we can easily handle random delay interrupts. Similar happens with clock jitters. Little bit more difficult than random delay interrupts, but again, on the right hand side, you can see that when we train clean noisy pairs and clean the data in that perspective, we can relatively easily break the target. For shuffling, here the technique how to improve the shuffling. So on the left side is actually adding more measurements to the training phase, and on the right side you see the convolutional autoencoder, but of course with smaller profiling set, and it works even much better, even with much smaller profiling phase, because we did the cleaning with the autoencoder. And now one can ask, well, this looks cool, but how do you do this? How do you do this clean noisy pairs? Because your target has countermeasure, how do you obtain the clean measurements? So one simple answer is, well, hopefully you, in the role of the evaluator of attacker, you have the access to the device under attack, so your profiling copy. So maybe you can disable the countermeasures, and then you can obtain the clean measurements. But also what you could do is something in the sense you could first do the classical technique. So for instance, for Gaussian noise, you could do averaging, and then not feed into your autoencoder clean and noisy, but clean and less noisy. So, noisy and less noisy. So one side has the noisy measurements, the other side has the averaged measurements. And you can still train your autoencoder with measurements like that. And here we show the results, what happens for Gaussian noise when you train from convolutional autoencoder from noisy to average traces, and what happens for desynchronization when you train from noisy to static aligned traces. So of course the performance is not as great as what you have when you train with noisy clean, but autoencoders can still work very well even if you train noisy, less noisy pairs. Interesting, I do not show results. We also tried the setup where we tried to clean already, let's say, clean traces. Because we asked the question, what happens? Would then autoencoder ruin the information? But no, autoencoder is capable of understanding that basically all information is useful information. So in that setup, autoencoder basically does nothing. This is very, very short on the topic, but you can see details in this paper. And finally, I'm actually...
Stjepan, we have about 5 minutes now.
How much? 5 minutes?
5 minutes, and then we would encourage some
5 minutes is plenty of time. So here, it's something completely different, public key crypto, protected with countermeasures, and then how can we do attack that works well? How can we do machine learning attack that works well? Well, first question is, what is the common attack that people would do in unsupervised setup for a target like this? So for instance, they could do something like horizontal attack, horizontal clustering. And then with attacks like that, if your target is very protected or high quality protected, your accuracy, so guessing bit 0, guessing bit 1, can be either good or not so good. So basically on the level of random guessing. And our question was, what happens in those setups where techniques like horizontal attack can give us the performance barely above random guessing? Can we plug that steal that results into machine learning and obtain better results. And for that, we played a little bit with ECC implementations from software-based protected implementations. And we used the horizontal attack, where basically our accuracy of the horizontal attack was 52%. So barely above random guessing, and not very much if you want to guess the whole secret value, whole private key. And then we said, well, let's try to combine it with deep learning. And we proposed a deep learning based iterative framework. How does it work? Well, here you can see the description. So you take your data set, you divide it into two parts, you train on one part, you predict on the second part, and you relabel the second part. Then you train on the second part, you predict on the first part, and you relabel the first. Then you combine the first and second, and then you shuffle the whole data set. That's your first iteration. Then you do your second iteration, and third, and so on, until your framework cleans the measurements sufficiently. So just to show you results, depending on how well do you do your framework, how well do you do your neural networks, we managed to go from 52% accuracy to 100% accuracy. So if your neural network is tuned enough and you apply the framework, you can actually obtain from almost random guessing behavior to 100% correct guessing. And yeah, here I show also, so these are for two different data sets. So C-swap pointer and C-swap arit data sets. So we can see that you can reach 100% very easily, starting from unsupervised approach. So horizontal attack, you take the stuff you have from horizontal and you ask your neural network to improve on that. Why this works? Well, first it works because we are still above random guessing. And second, because deep learning is capable to work well even in the presence of noisy labels. So in every iteration, we improve a little bit. Again, paper is available here for details. And finally, to conclude, yeah, challenges, there are many challenges. Let's say I leave this for your pondering in your own time. And to conclude, for implementation attacks, for side channel attacks, machine learning today represents the most powerful option, at least from academic perspective. So what is considered to be the most powerful from research side. What is interesting is that state of the art in side channel is usually much simpler than in other domains. What is also interesting is that state of the art deep learning in side channel is usually old. What do I mean by old? I mean techniques proposed like 10 years or so in machine learning community. And then this also opens a natural question. Can we actually reduce that gap? And can we start looking at the more recent developments in machine learning, in deep learnings, and also apply that to side channel? And when I say, can we do that without waiting for 10 years to have this decade-old results? And finally, of course, what is the big picture that I completely left not answered in this talk, and I do not know how to answer it. What do new attacks teach us about improving security of devices? Because we do attacks to improve the security. But the question is, after our successful attack, how do we improve the security? In my opinion, this is a very important question that we should try to understand and answer. And thank you for the attention. Q&A. Shivam, will I read and just answer?
I can read the question for you. So, so we have one question which basically asks that in context of DPA, that is more considered as a classical method, what is the difference between ML and DPA? Like, does the classical method need lesser traces or advantages and disadvantages?
So the difference is, the advantage is really that we need much less measurements. Ideally, with the machine learning or any profile attack, we would like the attack phase, so the phase where we are really guessing the key, that we need only a single measurement to break the target. Of course, in reality, you rarely get a single measurement that it's enough. But when you compare with classical approaches, they need, well, depending on the target, but from hundreds or thousands, tens of thousands of whatever measurements. Additionally, for classical techniques, people also commonly do run various pre-processing phase and feature engineering phases, while for more recent machine learning, so deep learning based side channel attacks, we also do not necessarily need those preparation phases. So I would say the biggest advantage is really much less traces.
We have another question. It says, for the NACL library that you were using for the ECC analysis, does it contain countermeasures for horizontal attacks, or like it is only countermeasures for DPA?
It contains countermeasures, exponent blinding, and one more. Let me check quickly. Let me stop sharing the screen. I know it's exponent blinding, scalar, and what more? Is it there? I'm sorry. Yes. So scalar blinding countermeasures. So it's yeah, just NACL library. I do not. Yeah. So it's based on a Montgomery ladder algorithm that is. And then how you do the conditional swap operation, that is constant time, of course.
Before going to the break, I have like one final question. Does your so the autoencoder part that you were presenting, was it used in a profile setting or non-profile setting?
Autoencoder. Well, autoencoder is non-profiled in that setting, but you of course have clean noisy measurements, so you could also consider it as a profile because the attacker has the information. It's just that you work only with inputs and clean and noisy inputs, so it's non-profiled.
So it can be done on the fly.
It can be done on the fly. Yes, depending also a little bit on exact setup and yeah, how or depending also a little bit actually whether you can really assume that you can turn the countermeasure on off. So otherwise you still need to play with those other techniques to first get less noisy and then plug into autoencoder. But what we notice is that autoencoders, even small ones, quite easily clean those types of countermeasures, those types of noise. So definitely, let's say it's on the fly and quite efficient. Not real time, but quite efficient. Any other questions?
I don't see any other questions appearing now, but I would encourage the audience to please feel free to ask questions. You can use the Q&A panel for privately asking the question, or you can use the chat if you would like to ask to the general panelists. So with that, Stjepan, I would like to thank you for sharing your talk. It was really interesting and definitely gives a very nice picture of how machine learning is used for science.